examples of when we have an integrand that is a ratio of a polynomial and also a variable base to a number power. This process is something we can apply when our denominator is just one term. So I don't have any other pluses or minuses in my denominator. Now when we're looking at this, we want to remember that when we were dealing with adding or subtracting fractions that had a common denominator, we would add or subtract the numerators and keep the common denominator. We can go backwards on this process if we're integrating, because remember, I can't integrate a pure function divided by a function. There's no integration rules that allow us to do that, nor will there be. So when I have that ratio of two functions, I have to see if I can rewrite it using either my operations algebraically or possibly even with other things that are going on with it in order to integrate it. Let's look at these examples. So in this first one, because I have the monomial denominator and a polynomial numerator, we're going to rewrite the integral as each term over that common denominator. So 5x to the 4th over 3x, then minus 2x over 3x, then plus 4 over 3x, and then dx. Now we want to simplify each of those fractions individually and rewrite any that we need to make sure that it conforms into one of these forms that we have our indefinite integral rule for. So in our first fraction, there's no common factor between the 5 and the 3. But with my variable base to number powers, remember if I'm dividing exponential expressions, I keep the base and I subtract the exponents. So this will be 5/3 x to the 4 minus 1 is 3 power. And then minus, well here there's no common factor between the 2 or the 3, but I can remove the common factors of x and I get 2/3. And then plus, no common factors between the 4 and the 3, but I want to make sure that I don't have this with the x in the denominator. We don't have any of the rules that go back to that. So I need to make sure I rewrite this as my letter base to my number power. And remember, that's the rule we use as long as n is not equal to -1. And if our exponent is -1, we'll use this rule. Well, look what happens. If I have this factor of x to the 1st in the denominator, when I rewrite it in an equivalent form where the x is in the numerator, I have to keep the base and change the sign on the exponent. So an exponent of 1 in the denominator is an exponent of -1 when you move that factor up. And I can do that because it's attached by times and I don't have any pluses or minuses between that. Now integrate this, we're going to integrate term by term. We have a rule of our indefinite integrals that allows us to do that. And any of them that have a constant factor multiplied to the integrand will bring that constant factor out in front of the integral sign. So when we apply that, we get 5/3 times the integral x to the 3rd dx minus 2/3 times the integral 1 dx, and then plus 4/3 times the integral x to the -1 dx. Now integrating these term by term, these are letter base to number power. So as long as the number power is not -1, we add 1 to the exponent and divide by that. So this will be an x to the power 4. And then when I divide by 4, it's like multiplying by 1/4. So I have 1/4 times that 5/3 and then x to the 4. Minus 2/3 times the integral of 1 dx. Well, the integral of 1 dx is x. And then plus c, but we'll add that constant all at the end. So that's minus x, and then plus 4/3 times the integral of x to the -1 dx. See, I can't add 1 to the exponent and divide by that because that would make me divide by 0, and we can't divide by 0. So what do we do when our exponent's -1? Well, the integral of x to the -1 dx goes back to the natural log of the absolute value of x. So this is the natural log of the absolute value of x, and then plus c. So overall I'll get 5/12 x to the 4th minus 2/3 x plus 4/3 times the natural log of the absolute value of x, and then plus c. Okay, how about the next one? These two problems are virtually the same, and we're going to do the exact same process. The biggest difference is here, because I have a radical in the denominator, I'm going to have a fractional exponent. So then when I'm simplifying my expressions and working with this, I'll be doing that addition and whole process with fractional exponents. So you just have to keep on your toes and remember what the rules of fractions are. So I'm going to have our integral of 5x to the 4th over 3x to the, now cubed root of x is the same as x to the 1/3 power. So when I change from radical to the fractional exponent notation, remember in the fractional exponent, the index of the radical is the denominator of your fractional exponent. And then minus 2x over 3x to the 1/3, and then plus 4 over 3x to the 1/3 dx. And just like before, now I'm going to look at the simplification of each fraction. So this is the integral of 5/3 x to the, okay, so 4 subtract 1/3. Well, 4, rewritten in a common denominator of 3, is 12/3. So if I take 12/3 and subtract 1/3, I'm at 11/3. And then minus 2/3 x to the, this is an exponent of 1, and 1 minus 1/3 is 2/3. And then plus 4/3 x to the, bring this x to the 1/3 in the denominator up, and it changes the sign of the exponent. So that'll be x to the -1/3 when you bring it up, dx. Now we're going to write this as term by term integrals and bring out the common factors. So that's 5/3 times the integral of x to the 11/3 dx, minus 2/3 times the integral of x to the 2/3 dx, and then plus 4/3 times the integral x to the -1/3 dx. Oops. Okay, now integrate each term. This is 5/3 times, add 1 to the exponent. 11/3 plus 1 is 14/3. So I have x to the 14/3. And when I divide by 14/3, it's like multiplying by 3/14. Minus 2/3 x to the, add 1 to 2/3, you get 5/3. Divide by 5/3 is the same as multiplying by 3/5. Plus 4/3 times x to the, add 1 to -1/3, you have 2/3. And when you divide by 2/3, you're multiplying by 3/2. And then plus c. So here my multiply across the top, multiply across the bottom, remove common factor pairs. I have 5/14 x to the 14/3 minus common factors of 3 will remove 2/5 x to the 5/3, and then plus common factors of 3 removed, you'll have 4 divided by 2, which is 2, x to the 2/3, and then plus c. Let's look at a couple more. How about the integral of 7e to the x minus x squared dx? Well, when I look again at the exponent, it's just an exponent of 1, so I just have these two terms. I can integrate term by term, and any constant factors I can pull out front. So this is the same as 7 times the integral e to the x dx minus the integral of x squared dx. Now when I look at this, I see if I have a basic indefinite integral rule for this case. Well, the integral of e to the x dx is e to the x plus c. And we'll do that plus the constant term at the very end. So this is 7 times e to the x minus, and this is a integral of x to the second dx, letter base to number power, and the number power is not -1. So we are going to add 1 to the exponent and divide by that. So this gives me x to the third power dividing by 3 is like multiplying by 1/3, and then plus c. So there wasn't that much rewriting that I had to do on this integrand. This one, however, is going to require us to do some rewriting because I don't yet have anything that allows us to integrate when there's an action on an expression, and I don't have anything that lets us integrate a product. So we're going to have to expand out the binomial, multiply through the x squared before we can integrate. So this is the integral. Taking this 3x minus 1 and squaring it, we get 9x squared minus 6x plus 1, and then times x squared dx. So remember, you have to do the extended distributive property when you're squaring out that binomial. Now, multiply through the x squared, because that's still multiplication. This gives me the integral of 9x to the fourth minus 6x cubed, and then plus x squared dx. Now I can integrate this term by term and bring the constant factors out. So this is 9 times the integral of x to the fourth dx minus 6 times the integral x to the third dx, and then plus the integral x squared dx. Finally, we're ready where it's been rewritten and we can integrate with our basic integral rules. And each of these are letter based to number power, and each of them, the power is not -1. So we are going to use this rule on it. So this gives me my 9 times, and then x to the add 1 to 4 is 5. And when I divide by 5, it's the same as multiplying by 1/5. Minus 6 times, we'll keep that base x, add 1 to 3, that's 4, divide by 4 is the same as multiplying by 1/4, and then plus, keep the base x, add 1 to 2, that's 3, divide by 3 is the same as multiplying by 1/3, and then plus c. And then with these multiplications of the constant that was there, times what you have as a multiplication from the integration process. This first one is 9 over 1 times 1 over 5, so that's 9/5 x to the power 5, minus 6 over 1 times 1 over 4 is 6/4, but there's a common factor of 2 top and bottom there, so that will give me 3/2 x to the fourth, and then plus 1/3 x to the third, and then plus c. Well, I hope these examples have been helpful in getting you a little bit more comfortable with the indefinite integrals. And I posted a couple prior to this that described what the indefinite integral is, and also some examples where there are trig functions in the integrands. So I'll put a link to those videos in the description of this video for you to go back and look at those if the problems that you're working also have the trig functions in them as well.